Welcome in the Printing and Coating Lab. My name is Deferme and I'm group leader of the Functional Materials Engineering Group, a research group in the Institute for Materials Research from UHasselt University. In this research, we focus on the engineering of functional materials that we deposit with different printing and coating systems. The first system I would like to show you is this inkjet printing system. It's a drop-on-demand inkjet printing system that generates droplets of around 20 to 30 micrometer. These droplets then are guided towards the substrate where we can make nice structures having a line width of around 50 micrometers and a thickness of around 200 nanometers. The materials we focus on are, for example, silver nanoparticle inks, graphene-based inks, PDOP-PSS, but also diamond nanoparticles that we, for example, use for heater applications. All of those inks are formulated in such a way that you do not only have the functional material, but also solvents. And to get rid of those solvents and make the final structure conductive, for example, we need ovens or near-infrared sinterings. So here you see the oven and a near-infrared sintering system, and we use these systems to cure our printed samples. If, for example, you print silver-based nanoparticle inks, you need the oven to go to 250 to 300 degrees centigrade. This means that for samples that are heat sensitive, like textiles and paper, you cannot use this oven, and we investigated the use of near-infrared sintering on these heat-sensitive substrates. Because with this system, you heat up only the printed lines and not the surroundings, such that your textile and your paper will not degrade. The next printing system that I show you is ultrasonic spray coating. This is our ultrasonic spray coating system, and if you compare it to inkjet printing, this system can deposit coatings on large area, where with inkjet printing we focus on printing of structures. The coatings we deposit here are functional coatings having a thickness of only 20 to 30 nanometers. And if you compare that with the standard spray coating techniques used in industry, which have a thickness of around tens of micrometers, you know why we need a lot of research to develop these functional coatings. One of the examples we research a lot are these organic light emitting devices. These OLEDs are built up of different functional layers on top of each other, having a thickness between 30 nanometers and 80 nanometers. And finally, if you apply a low DC voltage, this device will emit light. Another example, for example, is this sensor where you can measure temperature and strain simultaneously. And this one is deposited with this ultrasonic spray coating system on textiles to use in wound monitoring. And a final application that I would like to show you here is this sensor that is used for smart packaging, in which the PANI, the temperature dependent layer, is deposited with our ultrasonic spray coating system. The last technique we investigate is screen printing. With screen printing, we deposit viscous inks through a screen onto various substrates. And because these inks are so viscous, the final layer thickness is much thicker than, for example, with inkjet printing. With inkjet printing, we went to 200 nanometer thick layers, while with screen printing, the thickness is around a few micrometers. However, the benefit of screen printing is that the speed of deposition is much faster. And in comparison to, for example, inkjet printing, the line width is comparable and can go down to around 50 micrometers. An example of this you can see here, where we print metallic tracks used for interconnections in PV applications. Other applications that we do with screen printing are, for example, this antenna that can be used for smart packaging, or these light emitting devices that you can see here, where we print several layers on top of each other, and by applying an AC voltage to it, they will emit light. You can see that we print on flexible substrates, such as textile and paper, but we can also print on flexible substrates, and use these flexible substrates afterwards for 3D forming. Stretchable electronics is a hot topic in research nowadays. In our research, we focus on liquid metal as the conductor and embed electronic devices inside silicones to come up with what we call silicone devices. Here, for example, you see light-emitting devices embedded in a silicone and interconnected with the liquid metal, and we can stretch up to a few 100%. Other applications that we focus on are smart patches to monitor body properties, and the interconnection between the stretchable device and your flexible or rigid device is of crucial importance. As you see, the combination of different printing techniques such as inkjet printing, spray coating and screen printing is very important to come up with state-of-the-art applications. If you want to know more about the different printing techniques we use in our lab, you can find dedicated videos in our social media.